directional acoustics, and the LRAD. A long-range acoustic device, LRAD, creates a tightly controlled, focused beam of sound. Unlike traditional cone speakers that disperse sound outward radially, an LRAD utilizes a planar array of piezoelectric transducers. These transducers generate sound waves perfectly in phase. Through constructive interference, this creates a highly directional acoustic wavefront that maintains intense pressure levels with minimal dispersion over long distances. Cavity resonance mechanics. When directional acoustic energy is targeted at structural enclosures, treating the sinus or the roof of the throat strictly as physical geometric cavities, the interaction is governed by acoustic resonance. In the physics of sound, these spaces act as Helmholtz resonators. The frequency at which the air mass inside a specific cavity will naturally resonate is determined by its volume and the geometry of its opening, modeled by the equation, where v is the speed of sound in the medium, air, a is the cross-sectional area of the opening, v is the volume of the cavity, L is the length of the opening or neck. If the frequency of the sound waves emitted by the LRAD matches the natural resonant frequency of the targeted cavity, the amplitude of the pressure oscillations inside that space increases dramatically. Acoustic influence on fluid dynamics. The mechanical movement of air, such as a cycle of intake and expulsion, relies entirely on stable pressure gradients. Air flows predictably from areas of high pressure to areas of low pressure. Because sound is essentially a series of mechanical pressure waves, compressions and rarefactions, directing an intense LRAD beam into an active air passage drastically alters the localized fluid dynamics. Pressure disruption. High decibel directional acoustic waves introduce rapid, severe localized pressure fluctuations. This fundamentally disrupts the static pressure gradients required for a steady, laminar flow of air. Acoustic turbulence. The continuous compressions and rarefactions of the sound wave collide with the directional flow of the air column, creating extreme turbulence and air mass stalling within the passage. Mechanical impedance. The kinetic energy from the directional acoustic wave forces the air mass at the opening of the cavity to oscillate at high frequencies. This rapid vibration effectively acts as an acoustic barrier, mechanically impeding the continuous intake or expulsion of air through the channel.